Hey there, everyone. My name is Ryan Schul. Welcome to my data science channel. I started this journey back on back in August 8th of 2024. I've been doing this for about 180 days. I've got about 180 videos done at this point. I created a self-proclaimed goal of creating one video per day on average, and I'm trying to create 365 videos, not 100, 365 videos in one calendar year, and I'm pretty much right on par with where I need to be with that. So the journey continues, and we'll keep marching forward until we get to 365, and hopefully I can do it before August 8th, 2025. So this is a new series I just started. It's kind of short. It's about 5 lessons long, and in this series, I'm focusing on machine learning for environmental protection. And in this particular lesson, I'm going to focus on clustering techniques, and we're going to use Python and Jupyter Notebooks. Of course, for all my videos, I use Python and Jupyter Notebooks, almost all my videos. I mean, there's a couple on SQL. There's a couple of them out there about Excel. So that really has nothing to do with Jupyter or Python, but there is some overlap. If you work in the analytics space, you'll probably touch on SQL Server almost without question. You're going to have some exposure to that, and Excel too. Neither one is going away, but primarily I think most things are done in Jupyter Notebooks, but there's exceptions to sometimes we use databases like SQL Server or other databases, and sometimes we actually use spreadsheets. Believe it or not, spreadsheets are not going away. So I think the more comfortable you are using spreadsheets, the better off you're going to be. So anyways, let's focus on the topic at hand here. This is clustering techniques. We're going to use Python. In this case study, we're going to look at relationships between city size and the environmental impact, and we're going to use some different machine learning strategies or methodologies to answer some questions and get more insight into this data set that we have, okay? So machine learning for environmental protection has a lot of applications: urban energy planning, renewable energy integration, industrial process optimization. I just finished a video about optimization. That's very interesting. You should check that out. Transportation optimization. In that last video, I talked about that as well. And then building energy efficiency, creating HVAC systems, improving the smart grid, things like that, right? So let's jump into it. Enough intro. Let's jump in and go all in on this teaching lesson and see where we go. Okay, so Control Enter to refresh it. This is a simple data frame that I created. Now I looked around for sample data to help me answer the questions I want to answer. I couldn't actually find the data. I didn't spend tons and tons of time, but I spent a little time. I couldn't find it, so I created the data set. So if you look closely, these are NP, NumPy random choices, and I'm setting like an upper and lower limit and telling the computer, or telling Python, go ahead and create these data sets for me and combine everything into a nicely structured data frame. That's where I got this. So again, if you can find the data, that's great. I spent some time working on it, couldn't find it, and gave up and just created my own because I had some ideas I wanted to test. And if I couldn't get the data, I couldn't do the analysis, right? If you don't have the data, you can't do the analysis. So you have to get it somewhere, either find it, reach out to somebody, get some discussion going. Do you know where I can find this? Do you know where I can find this kind of thing? Or just create your own. So I ended up creating my own. So here we are. We can encourage developers to construct new homes close to offices, schools, and shopping areas, right? So if your house is close to your office, close to your school, and close to your shopping area, you don't have to commute too far, and you don't have to spend a lot on commuting costs or spend a lot of money and create a lot of emissions into the environment, right? The closer you are to where you need to be, the less emissions. We can use geospatial data to make or model understand different commuting patterns and optimize those patterns. You'll see an example of that in just a minute. We can create clustering algorithms or clustering techniques to find optimal areas for creating new housing projects, right? If there's going to be a new condo development created or whatever, we can create this kind of in the middle of where other people live, or kind of in the middle of where people go to school, go out for recreation activities, go to their office, things like this, right? We can find places that are relatively close to where you already are and build there, rather than building way out in no man's land and expecting people to commute long distances to get there, okay? That doesn't make a whole lot of sense, and I'll prove that to you using a couple machine learning techniques right here. So we have home latitude and home longitude again. Ideally, you want to find this data somewhere in a CSV, some website, an Excel file or whatever. I couldn't find it, so I just created it. So here we are looking at city size, population, population density, industrial activity, transportation, renewable energy. I'm not going to read them all. You can read by yourself. Everybody here is literate, right? And perfectly capable of reading those. So, but that's the background. That's why I set this up, and I'm trying to solve these problems based on longitude, latitude, commuting distance, and then transportation modes. Okay, so let me hit Control Enter to refresh this. We'll have all the updated data here. So we have the latitude, longitude for home, for work, commuting distance. That's the distance between those, right? And then the transportation mode, bike, bus, car, could be light rail, so on and so forth. Okay, so now we have a full name map. I love these full name maps. They're very user-friendly. You can zoom in, you can zoom out. You can click on the map and you can get some details. Oh, this one doesn't have it. Okay, and the next couple of maps, I do have some details embedded in there. So when you click on the push point pin here, or whatever it's called, indicator, icon, I think it's called icon, yeah. Full name icon, that's it. So we have blues and reds. So blue would be house, red would be kind of destination. Like here's middle school. This is in Boulder, Colorado. Okay, so it's at the foothills of the Flatiron Mountains, the Rocky Mountains. The Flatiron is kind of like the eastern border of that. I went there a few years ago. Absolutely fell in love with the city. Wanted to move there, but that never really worked out. But whatever. We have the map of downtown Boulder and surrounding areas. Now this is kind of randomly generated. Again, I couldn't find the data that I wanted, so I just dumped this into a Python notebook and said, Python, you create the data for me. And you can see it's very random. People are scattered all over the place. These people over here, if I zoom in, looks like they live inside of a tree house. Okay, I don't know if anybody's living in a tree house. These guys down here live also in the middle of nowhere. I don't even know what that is. So the first time I created a data set, I almost deleted it, but I actually kept it. I thought, okay, this is what I don't want to do. Let me share it with other people. You don't really want this. You want to be a little bit more realistic. Okay, so think about the problem you're trying to solve and then think about the solution too. This is just random data. Blue indicates a house. Red indicates a place where people congregate. So it could be a school, a hospital, a house of worship, church, right? It could be a recreational facility with a swimming pool and gym facilities, could be even a shopping mall, anything like that. But it has to be kind of realistic too. This is sort of random. I could have deleted it. I didn't. I left it in there just so you can see what not to do. Okay, so you don't really want to do this. You want to create the maps so it's a little bit more realistic. The people most likely will live in these higher densely populated areas that have been cultivated for living. Right over here, everything that's green is basically, I think, either a national park, no, not national, probably a state park, or maybe a local park or something. Anything that has this green, light green that looks like a lemon, I mean like a lime. It's all woods. It's all dense wilderness, right? So we're not probably building houses there. Maybe not too many, maybe one or two. But most of the people will be more in the municipal area. So don't set up your machine learning data set like this, because that's kind of arbitrary and random, and the results are going to be arbitrary too. You want to be a little bit more meaningful. So I'm going to cut down the number of commuters. I think we had 100 before. I think that's what it was. We're going to get more realistic latitude, longitude. This is slightly south and east of downtown Boulder, and this is going to be in the suburbs of downtown Boulder. So you have a beginning and ending threshold for the longitudes, and again, beginning, ending threshold for the latitudes. So let me go ahead and create this. So rather than just pure randomness, which is what we saw in the first example, this is going to be slightly more realistic and more thought through and planned out. Okay, so we can see the asterisk is running, and we have the hourglass in the upper left-hand corner of the notebook. So you can see that this is running right now. Hourglass indicates that we need to wait, right? That's a timer, I guess. It looks like an egg timer, kind of. So still running, and we can see the asterisk right there, just above the import. So we'll give that a minute to finish off. And let me take you through what we're doing here. We have a couple different random types of vehicles that we can use to commute from point A to point B: car, bus, bike, walking. Okay, in the downtown Boulder area, it's it's highly likely that you could walk from where you work to wherever you're going, your office, your grocery store, uh, shopping center, whatever it is. That's feasible. If you live way out far away from these areas, then maybe walking isn't an option. In Boulder, it definitely is an option. Okay, biking is popular, walking. So we have these as transportation modes. So here's the data frame. And we have the latitude, longitude. So that looks great. Let's go ahead and plot this on our folium map. Again, folium maps are great because they let us zoom in, zoom out. We can see all the details of the map. We're going to get all of our latitude, longitude coordinates, and then work and home too. Okay, so we want to see where people live and where people work. And based on those two, we can figure out the distance that they have to travel to get from home to work, right? So it's pretty straightforward how everything goes here. And the home will be indicated by a blue marker, and red will show us downtown areas. Okay, and the folium map is going to pop up. So now we have more realistic homes here in the areas that have been created for houses, right? So this has been sculpted or cultivated or created with all the roads, the streets, the houses built out. Again, we're trying to avoid this dense wilderness over here. Although you can see there's some houses, right? But it's kind of on the edge of suburbia. It's not like way, way over. If you keep going west over here, there's not too many houses, right? And this is just forest over here. So let's just keep it realistic for now. With houses, if I click on each house, it tells me the number of the house, right? And then we have the downtown work center here in red. So blue is house, red is office space. And if we zoom in, another thing I love about these folium maps, we can see all the details here for the streets, right? We can see United States Post Office. There's a post office right there. That is Colorado Building. Smile Direct Club. That is probably a dentist's office. You see a bank right there. And then all the streets and the contours of the streets. This looks like a small city park. And you can see a small creek running through the city, and then like a boulevard, Canyon Boulevard over there. Okay, so it gives you some extreme details. Very nice, very interactive, very intuitive as well. Okay, so we have the streets, we have the people's houses, we have the work location. Let's take it up a notch further and go to the next step of this analysis. So network-based shortest path uses geospatial clustering, k-means clustering, and spatial analysis, including Dijkstra's algorithm. So Dijkstra's algorithm shows us the shortest distance between 2 points if you're trying to optimize the distance or just find like the shortest distance between 2 points. You can look at this view over here. Let me go back a little bit. It's going to be a straight line. The shortest distance between 2 points is defined as a straight line, right? That's a mathematical definition, sorry. And that's not negotiable. But like a lot of times, if you are traveling on roads, you can't take a straight line, right? You have to follow the contour of the road. So this guy that lives in this house, house number 9, he's going to have to go down Upland Avenue. Okay, it looks like he's traveling west. I think that's west, and then south on 19th Street. So you go south for a little bit, and then you go west, southwest, south, then southwest, kind of, then south, and then south on Broadway, and you get to your office. Okay, so that is the shortest path. We use Dijkstra's algorithm to get us from point A to point B, and the shortest distance in the shortest time, presumably, as long as there's not a lot of traffic on that route. And again, we're just looking for efficiency, right? So shortest path, and this is a network analysis type of problem. So let's go ahead and run it. Control Enter to refresh the cell. Okay, and do the network analysis. This is going to give us the graph from the place. This is a city center, or the focal point for this analysis, right in downtown Boulder, Colorado. We have the home nodes and the home coordinates and the commute routes. Okay, so we have the routes here. And again, this is all based on longitude and latitude logic. And we're going to add in coordinates, right? And blue for home. And we're going to add a pop-up control here. If you look in folium maps, you can Google this. It's very fascinating, I think. www.google. Whoops, I just had it and just deleted it. Folium maps. Pop-ups. There's all kinds of details around folium maps and all the documentation. So you can see here, what they give you, and then you can click on that and interact with the map, right? So pop-ups is one control. These push pins is another. You have layers, you have icons, all kinds of different stuff. So I'd highly encourage you to get into this Folium Maps, look at the sample code that they give you, copy and paste that into a Jupyter Notebook, and just work with it and just see what you can do with these maps, right? That's the best way to learn. Just explore, experiment, test it out, and see where you go with it, right? Here's detail. I live in New York City, or just outside of New York City in Queens, actually. And this is a detail of my neighborhood. And again, you can see all the roads, the street names, one-way streets. This is a one-way. This is a one-way going the other way. So it's very interactive, very intuitive in the way that these maps work. So you have the home coordinates popping up. We have another pop-up. That's the downtown center. And in another pop-up I created, this is really cool because you have just a couple of different parameters that you put in. You have .add to property M is going to be short for map. So you keep adding to maps. We create the map here. That's the raw map. We're adding in the downtown location. We're adding in coordinates. These are latitude, longitude coordinates. We're adding in distances to the map, right? So you always have this property .add to and then M in brackets. And then we have clusters. We're going to create a cluster. So all the houses that are substantially close to each other could be in one cluster. If you're different, you go into another cluster, right? Those are either homogeneous or the same, or heterogeneous if they're different. Okay, so everything's going to go into one cluster if they're homogeneous, and a bunch of different clusters if they're heterogeneous. And the point is you keep on adding to this M variable, and you add just layer after layer after layer after layer. You keep going until you get to the last layer here. For me, the last layer is the address and the text that you're adding to it, and everything becomes M. So you take all this stuff and roll it into M, which is the map, and you can see the clusters here. So if I click on this house, I can see cluster 5.0. This is home number 9. This is home number 15, cluster 1.0, and this is the address, 425 Utica Avenue. If I zoom in, we should see exactly the same thing. Okay, and Utica Avenue, there it is. Number 425 Utica Avenue, right? And this is cluster number 1. The line goes off the road a little bit. It's not perfect, but you can see it pretty much follows the line. Like they kind of cut some corners here, literally, when they're defining the way these polygons line up. But you can see when it's straight, it's much more accurate, right? When you have sharp, tight corners, it's a little bit off, but by and far, for the most part, it's pretty decent. Like this one follows the contour of the road pretty close. This is cluster 3. And again, 2695 5th Street. If we zoom in, it looks like 5th Street right there. So 5th Street is north and south. 2695 is the latitude, longitude coordinate. And you can see that the circles represent the different clusters, right? So these houses here are in one cluster. And the point of this is to try to find areas where people are congregated in certain concentrations. And if we're going to build a new residential space, like a new condo building with a bunch of units, maybe 50, 60, 100 units or whatever, it's going to be kind of in the middle of where all these people live, because all these people, well, they actually live in a house now, but I mean, if you need new construction, you would look at the proximity for where most people live and then where they need to go, the downtown center where they work, right? And build your condo building relatively in the middle of these different clusters. So here's cluster 1, here's cluster 3, and we have a couple more, cluster 5 and cluster 6. So again, if you're a developer and you're looking to build new condos, you would find these clusters where most people are congregated. Where do they live now? Where do they need to be for work, school, recreation purposes, church, shopping, and build the condo building relatively close to where the people are now and relatively close to where they need to be. That's the whole point of this clustering algorithm. And then ultimately to reduce emissions, to help people get from point A to point B faster. Okay, so you save time, you save emissions, and it's win-win. Everybody wins, right? We're all better off for this. So here's one more thing I'll show you here. Control Enter to refresh it. This is a visual representation. Again, cluster 6, 5, 3, 1, and then the residential address is 1551 21st Street. If I zoom in, 1551 21st Street. Okay, so it kind of looks like an intersection of Arapahoe and 21st, but based on the lat long coordinates, it's 21st. Okay, so again, I made up some of this data, so not saying it's going to be absolutely perfect, but it should be pretty close. And if you get actual latitude, longitude coordinates, actual housing coordinates, and number of people in the residential, like all urban planners will have this data. I don't work in urban planning space. I work in the finance area, so I don't have this data, but you should be able to get access to this if you're doing this type of analysis. This is more for fun and just educational purposes, but if you're actually doing this to cut down on emissions, to actually cut down on people's commute times, and you're working with a developer and you're investing tens of millions of dollars, I guarantee you will get this data some way or some form. You will find access to this data, right? Because that's going to save you a lot of money, and you can make more accurate predictions once you get access to more accurate data. So this is a little bit made up, but again, it's pretty accurate. So you can see the clusters here, and then the addresses for each cluster. So cluster 1, 425 Utica Avenue. If I go back here, I think that was the one. Yep, that's it. Cluster 1, you can see right there, 425 Utica Avenue. So you can see the cluster, and this guy's by himself. There's no real circle around him because he's all by himself there. And I think another one was by himself, cluster 3. But maybe that was the downtown area. I don't know. Downtown? I don't recall seeing cluster 3 because we have 1, 3. Oh, there is 3. Okay, so here's all the houses in cluster 3, and again, you'll have the address for each one. Forest Avenue, I can see it, even though it's zoomed down a little bit. So Forest, this guy lives here, and actually, he's in cluster 2. He's actually in cluster 2. And this guy's in cluster 2 too. Okay, so I think this cluster 3 might have been a mistake. To check into that, because all these guys are cluster 2. I think there's one little issue with the logic here. Okay, but anyways, I would trust this a little bit more than trust this. Or maybe this just didn't refresh, because I think we had a previous example of that over here. Yeah, I think something didn't refresh, or maybe there's a minor miscalculation. We can swing back and fix that. But by and large, this is pretty accurate. Okay, we might have found 1 or 2 little warts. We can handle those warts, cut those off, or cover it up using some plastic surgery or something. Okay, but anyways, I think we're pretty much spot on with the analysis. Shakes out, it pretty much jives with what we'd expect. Okay, so again, any type of optimization algorithm is looking for some type of optimal outcome. In this case, probably commute time to work, right? Minimize the commute time. And when you do that, you'll have the dual benefits of minimizing commute and minimizing emissions. Whether you drive or take a train, doesn't matter. If you're close enough, you can walk or even take a bike, and then you'll have 0 emissions. So it's win-win. Close to work, less commute time, less emissions, win-win-win. What else? Initial population that was randomly generated, but should be somewhat realistic. The more accurate your data, the more accurate your predictions, the more accurate your analysis. There's a fitness function built into these algorithms, right, where the average commute distance is based on the current home location and the distance from work, right? Commutation is randomly alters home locations to explore a new solution. So that's another thing. If we don't have a lot of homes built, we can find the center of the cluster of homes, if it's just a few, where it is now, and then create an algorithm to do, it's called, what is it? Random mutations, or, oh no, it's a genetic algorithm that creates mutations of scenarios to say, okay, a few people live here, a few people live over here. Eventually, over time, the population is probably going to move in this direction or this or that or the other thing. That's going to skew one way or another. And these genetic algorithms can help us understand how population is going to change over time, increase, maybe decrease, or shift to the northeast part of the city, the southwest, northwest, southeast, whatever the case may be. We can create some randomly generated scenarios to see potentially where populations can shift over time as neighborhoods become more gentrified. Maybe more people will move there, or maybe move away. Sometimes neighborhoods don't gentrify, right? And people move out if it becomes a little bit more sparsely populated and subject to crime. People might move and migrate to a new area. So we can create hypothetical scenarios where we can track those potential movements of households over time too. So that's pretty much it. Just wanted to take you through that, guys. I'm going to go ahead and save this as an HTML file. I will upload the file to Google Drive, and I'll upload this video to YouTube in just a bit. As soon as I have time, I'll upload both the video and the notes, all these scripts here. You can copy and paste it, make some changes, and see what kind of effect that has on your analysis. That's why I like to share the scripts with people, because I do it for my own knowledge and my own edification, but I'd like to share it with you guys so you don't have to go ahead and type all this out. You can copy and paste it and run it almost immediately and start to run these experiments and see what the outcome is, and then make changes, modifications, and improvements, and see what kind of impact that has on your overall analysis and your clustering techniques and understanding environmental protection. Okay, so that's it. I'm going to wrap it up. Thanks for your time today, guys. I will see you in the next video. Keep an eye out for that. Thanks. Bye.